Okay, example 7 is very similar to example 6. We still want to find an orthogonal matrix P such that P transpose AP diagonalizes A, and then I'm going to verify that P transpose AP gives the proper diagonal form. So I started this already. We're basically starting the exact same way we did the previous problem. Find the eigenvalues, and I got this ugly mess, which gave me this trinomial. And if you don't remember how to factor trinomials using the rational zeros theorem, see the other video I did on exactly how to factor this guy, and you'll get lambda minus 2 times lambda plus 1 squared equals 0 as your characteristic equation. So your eigenvalues are 2 with multiplicity 1 and negative 1 with multiplicity 2. So then I said, alright, let's find the eigenvectors for these guys. Okay, so for lambda equals 2 for the first eigenvalue, I did all the work. I got this eigenvector, which was 1, 1, 1 times r, where r is any non-zero number. I normalized it, so square root of 1 plus 1 plus 1 gives me square root of 3 as my denominator, so I just had all of these guys divided by root 3. Alright, so that brings us to step 3. And this is where this problem is different than the previous example. Alright, so we consider the eigenvalue lambda 2, which was negative 1, and that had multiplicity 2, so that's why we're doing this in a separate step. Okay, so again we want to find the eigenvectors for this guy, so take negative 1 times I minus A, and we take a look, negative 1 minus, the main diagonal of A was all 0, so negative 1 minus zeros, and then the rest of A was all 1, so you have 0 minus those. You're going to get a matrix that consists entirely of negative 1s. So if you row reduce that, all you're going to get is a matrix that has 1s on the top row, zeros everywhere else. Alright, so in this case we only have one leading one. We used R up above, so I'm going to use S and T for my free variables. So I'll say x2 is S, x3 would be T, so x1 would be negative S minus T. So the x2 vector, I'm going to break into two column vectors. One is a multiple of S, one is a multiple of T. So we have negative 1, 1, and 0 S's. And for the T we have negative 1, 0, and 1. And again, these are for S and T not both equal to 0. We like to normalize these guys, but we also want to make sure that they're orthogonal to each other before we even normalize them. If we take a look at the dot product of this column vector and that column vector, we'd get 1 plus nothing plus nothing. So their dot product is not equal to 0 like we'd like it to be. So I'm going to use the Gram-Schmidt process, and it doesn't matter which one you call it, V1 or V2 in your Gram-Schmidt process. Just to show you it doesn't make a difference, let's call this V1. Actually, I'm going to call this V2 and I'll call this V3. There will be no V1 because we have a P1 and an X1 up above that correspond to the lambda 1, so let's call these V2 and V3. So I'm going to use Gram-Schmidt to find an orthonormal basis for those two vectors. So W2 would be V2, which was negative 1, 0, 1. And then W3 is V3 minus its projection onto W2. So I guess I'll write it this way. The projection of V3 onto the previous result W2. So V3 we said was this vector -1, 1, 0 minus its projection onto W2. So we're going to have -1, 1, 0 dotted with W2 over W2 dotted with itself times W2 so we get -1, 1, 0 minus, okay, this fraction would be, let's see, +1 plus nothing plus nothing, +1 plus nothing plus 1. So we get a 1/2, -1, 0, 1. So if I take -1 minus a half of -1, so it would be -1 plus a half would be -1/2. 1 minus a half of 0 would be 1. And 0 minus a half of 1 would be -1/2. Alright, then we want to normalize those two vectors, W2 and W3. And we're going to call those normalized vectors P2 and P3. So P2 will be W2 over its norm. So -1, 0, 1. And the norm of this will be square root of -1 squared plus 0 plus 1 squared, so it'll be square root of 2. So -1 over root 2, 0, 1 over root 2. And then P3 would be this vector over its norm. And if you take my word for it, I did the work ahead of time. The norm is square root of 3 over 2. So I'm going to get the W2 vector over its norm, which was square root of 3 over 2. And after doing a lot of algebraic simplification, I finally reduced it down to -1 over root 6, 2 over root 6, and -1 over root 6. Alright, so we have, from up above, we have our P1 vector. Here's our P2 vector and our P3 vector. Then step 4 says just take each of those P1, P2, and P3 vectors, form your P matrix using those three as columns. So altogether our P matrix for this example, the P1 vector was 1 over root 3, 1 over root 3, 1 over root 3. P2 was -1 over root 2, 0, 1 over root 2. And P3 was -1 over root 6, 2 over root 6, and -1 over root 6. And then the last thing we should do is verify that P transpose AP gives me a diagonal matrix, and that diagonal matrix should have the eigenvalues down the main diagonal and zeros everywhere else. And I leave that check to you.